I'm Arthur C. Clarke. I write science fact and science fiction. You may know my movie 2001: A Space Odyssey. I've seen some remarkable developments and inventions in my lifetime, but one of the most extraordinary is the Mandelbrot set and fractal geometry. Now we'll begin our serious exploration of the Mandelbrot set, a voyage which in fact could last forever and ever, much longer than the lifetime of the universe. I have here the full set, about 6 inches across. Now, if I blow this up, I'll increase the magnification now 13 times, and you see more and more detail is appearing. And the interesting thing is you see mini Mandelbrots, replicas, almost identical, yet perhaps subtly different, of the original set. And I can go on doing this. Here's a magnification of more than 3,000 times. So the original picture, about 6 inches across, is now half a mile across. And no matter how much we magnified it, a million times, a billion times, until the original set was bigger than the entire universe, we would still see new patterns, new images emerging, because the frontier of the M set is infinitely complex. And when I say infinitely, I really mean that. Most people, when they say infinitely, they mean only rather big, but this is really infinity. What is so remarkable, in fact, astounding, about the Mandelbrot set is that although it's infinitely complex, it's based on incredibly simple principles, unlike almost everything in modern mathematics. In fact, anybody who can add and multiply can understand the principles on which it's based. You don't even have to subtract or divide, still less use logarithms or trigonometrical functions to comprehend how the Mandelbrot set is created. In fact, in principle, it could have been discovered any time in human history, and not merely in 1980. But the problem is this: although it's only based on adding and multiplying, you have to carry out those operations millions, billions of times to create a complete set. And that's why it was not discovered until the era of modern computers. It was on the 1st of March, 1980, at IBM's Thomas J. Watson Research Center in upstate New York that Benoit Mandelbrot first glimpsed the M set. The seeds of this discovery were, in fact, sown decades before the M set was first seen. In Paris, in 1917, a mathematician called Gaston Julia published papers connected with so-called complex numbers. The results of his endeavors eventually became known as Julia sets, although Julia himself never saw a Julia set. He could only guess at them, and it wouldn't be until the advent of modern computers that Julia sets could be seen for the first time.
For me, the first step, or most difficult mathematical problem, was to program it and see how it looked like. We started programming Julia sets of all kinds. It was extraordinarily great fun. And in particular, at one point, we became interested in Julia's set of the simplest possible transformation. Z goes to Z squared plus C. So Z times Z plus C. I made many pictures of it. First of all, the first one was very rough. But the very rough picture, that was not the answer. Each rough picture asked a question, so I made another picture, another picture, another picture. And after a few weeks, we had this very strong, overwhelming impression that this was a kind of big bear we have encountered. I think the most important implication is that from very simple formulas, you can get very complicated results. It's fundamental from viewpoint of the very base of science, because what is science? We have all this mess around us, things are totally incomprehensible, and then eventually, more or less rapidly, more or less hard to achieve, we find simple laws, simple formulas. In a way, a very simple formula, Newton's law, which is just also a few symbols, can, by hard work, explain the motion of planets around the sun and many, many other things. The 15th decimal. It's marvelous. A very simple formula explains all these very complicated things.
There's an interesting parallel with the equation that almost everybody is familiar with, the only equation almost everybody is familiar with, E equals mc squared, Albert Einstein's equation that says matter and energy are equivalent to each other. That was a very simple equation with very far-reaching consequences. And the equation for the Mandelbrot set is equally simple. Z equals Z squared plus C.
The letters in the Mandelbrot equation stand for numbers, unlike those in Einstein's equation where they stand for physical quantities, mass, velocity, energy. The Mandelbrot numbers are coordinates, positions on the plane, defining the location of a spot. Another difference from Einstein's equation, and a very important one, is this double arrow. It's a kind of two-way traffic sign. The numbers flow in both directions, constantly feeding back on themselves. This process goes on and on and on. When the Mandelbrot equation is given a number representing a point, and that number is iterated through the equation, one of two things happen. Either the number gets bigger and bigger and shoots off to infinity, or it shrinks to zero. Depending on which happens, the computer then knows where to draw a boundary line. So what we get from this basic iteration is a kind of map, dividing this world into two distinct territories. Outside of it are all the numbers that have the freedom of infinity. Inside it, numbers that are prisoners, trapped and doomed to ultimate extinction.
Think of a computer screen. You're looking at each individual little element, each pixel of the screen. You pick one of these pixels, you apply this rule lots and lots of times, and either the pixel moves off and disappears completely from view, or it moves in towards a fixed point in the middle of the screen. And what you do is, you just want to distinguish between going off out to infinity or going into zero. So any point that moves into zero when you apply this rule, you colour that point black. And any point that goes off to infinity, what people tend to do is colour it all sorts of wonderful rainbow hues about how fast it goes away. The important bit's the black bit in the middle. That's all the stuff that doesn't escape when you keep applying this rule.
Now, the colors are completely arbitrary. They could be anything, but they are not meaningless. A very good analogy is the contour map, you'll see, of a mountain range, for example, where the contours are drawn and colored, the areas are colored. The highest areas might be colored white, then brown, then green, then if you went on into the sea, deeper and deeper blues, just to show where the various levels occur. So it's the same here. You can make the colors anything you like, but they do define the different areas of calculation. And you can change them and get the most gorgeous results.
The word fractal means any geometrical structure that has detail on all scales of magnification. No matter how big you make it, you still see extra new details you didn't see before. And the name was actually invented by Mandelbrot himself. He felt he had to have a name for this area he realised he was working in. And so he coined the term fractal because it conveys this feeling of fragmented, broken, fractional, irregular.
It took a long time for us to emerge and start to look out at the other part of the physical observable universe, not as narrow studied little entities, the scientist who studies the flea on the back of the flea on the back of the flea, but rather being able suddenly to look out at the totality of nature and then say, my goodness me, we've got nothing to describe this with. Clouds are not made with straight edges. Trees are not circles. They're not triangles. They're something very, very different indeed. But there's a continual kind of a pattern that I can see as I look at the edge of a rising cumulus cloud, one of those very, very wrinkly, coruscated clouds that has such fine structure in it. And you say, but there's no lines or circles there. The wonderful discovery has been that there's an extension of classical geometry, Euclidean geometry, which is called fractal geometry.
Fractals are shapes which we are extraordinarily used to in, how to say, our subconscious, ill-organized life. For example, everybody knows that if you take a map of Britain on a small school globe, you see a very simplified shape. Cornwall is just a kind of triangle, and Wales perhaps a little rectangle. You cannot put the details on a small map. If you look at in a larger map, you add more detail. The closer you come, in a certain sense, imagine yourself like somebody coming on a rocket. From far away, you see very little. And the closer you come, the more detail you see. If we come very, very close, you begin to see rocks, and finally the idea of coastline disappears, because one doesn't know any longer where is land and where is water. So indeed was arose in my mind to put together a geometry based upon many known facts in mathematics, scattered facts in mathematics, many scattered facts in our experience, many scattered facts in the results of what scientists had done of various kinds, as bricks, if you will, of a new building, which is a new geometry, which is a geometry of shapes which are equally rough at all scales.
One of the revolutions in thought that's resulted from this discovery is the realization that nature deals not in smooth, continuous objects, as we always imagined, but more often in fractals. And I'd like to show you how she does this. Now I'm going to generate a fractal before your very eyes. What you see here is what's called the seed, and it's an appropriate word in this case. Those two lines represent the first generation of the formation of a geometrical figure. And the computer has been told to continue growing these lines, but changing the direction every so often and at different distances. Now that's a very simple set of instructions, but look what happens after they've been carried out for, say, 10 generations. The tree I showed here, and it does look very much like a tree in nature, is symmetrical because the two branches at the beginning were the same length, off in the same direction. But if we change the length of one branch and change the direction, look what happens. In a way, this is a more realistic tree than the first one, because in nature you seldom have perfect symmetry. Much more elaborate structures can be created by very similar rules. I'd like to emphasize that all these shapes or objects, or whatever you call them, although they look real, are generated entirely in the computer by following out a few simple instructions and repeating them over and over again. This is the way in which nature creates things.
It's exactly like the DNA in a butterfly's egg. Somehow that unravels and unrolls to form the extraordinary and beautiful pattern on a butterfly's wing with its myriads of colors and form. Somehow it's hidden in that seed, in the DNA, and not only that, but the wings themselves probably only occupy a relatively small part of the total DNA. They are, if you like, a little formula that is unraveled by the process of growth and deterministic following of rules to form this natural.
Simple rules, simple laws of physics and chemistry. And a lot of the structure that you see in living creatures, this organic structure that the Mandelbrot set has of, you look at little pieces of them and they have lots and lots of detail. And in fact, the little pieces look very similar sometimes to the whole thing. It's very tempting to compare the way a simple formula produces a complicated Mandelbrot set with the way very tiny things in nature produce complicated organisms. And there are certainly some similarities in that there is the same kind of unfolding of a process. The instructions are there, but not an actual description of the object.
Once you develop a fractal geometer's eye, you can't help but see them everywhere. Every single thing you see is one way or another described by reference either to itself or to something else in the picture you see. It's as though you're staring at a vast dictionary, but the dictionary words are bits of pictures, and the references, the definitions of the words, are made with other bits of pictures. And so you stare at one picture. I look out in the garden and at the trees, and I see this set of relationships between the picture and other bits of the picture. Those relationships are no more nor less than the assertion, from my point of view, that what I'm seeing is fractals everywhere.
Atlanta, Georgia, headquarters of Michael Barnsley's Iterated Systems. In 1991, Barnsley received a $2.5 million government grant to develop fractal image compression systems. Corporations such as Microsoft, Mitsubishi, Multicom, and Virgin now use Barnsley's image and data compression software.
One of the most exciting moments occurred when I discovered the collage theorem. We'd been trying to work out how you could control a certain class of dynamical systems to make pictures of leaves. Then, struggling with the question, it just dawned on me that it was very simple. You needed to form a collage, a covering of the object, with copies of itself, smaller, shrunken copies, so that the whole object and cover it with little triangles. You might take a square and cover it with little squares. Well, the theorem said if you took a fern and covered it with little ferns, then you would have created a dynamical system or a formula for a fern. But if you tried to actually create a picture using the collage theorem, it took hundreds of hours of graduate student time working on the problem. And the holy grail at this point for us became the question of, could we find a way to tell a computer, just look at a picture, a digital picture, and automatically go ahead and find the fractal formula for it. The discovery of how to automatically calculate the collage for an arbitrary picture came to me in a dream. From the early days of doing mathematics, I used to have a recurrent nightmare, which was something to do with studying matrices. And they kind of remind one of perhaps an old-fashioned telephone switchboard. Well, in the dream what happened was there was thousands of holes and lots of wires connecting everywhere to everywhere, and it was always a sort of tense muddle between the switchboard with all the wires going everywhere, always in a horrible tangle, and somehow it represented a matrix. I'd had this nightmare many, many times over 20 years. Night of the anniversary of my father's death, 2 years after, suddenly I saw in the dream how you could straighten out the switchboard, how all the wires would become untangled and nicely connected, and how you would join all the wires from big blocks to little blocks in the grid. And I woke up in the morning, I knew I'd discovered it, that this was it. This was the total secret to fractal image compression. how to automatically look at a digital picture, these ones made of the low resolution input, like your eye receives, and how to turn it into A, a formula, and B, an entity of infinite resolution. So the goal is now to be able to capture this fire of Prometheus, if you like, this fractal wonder, put it in a box, and being able to make this.
Now compress images, so they require drastically fewer bits to store them. Now, whether you compress or expand an image depends on the same fractal principles, and Barnsley's theories have now become a commercial reality. Let's take a look at one of his programs. If we take a tiny piece of this image, which has been stored in digital form in the normal way, and blow it up, it becomes very pixelated, and they're huge pixels. Now, if we take this very coarse image and pass it through Barnsley's fractal analyzer, we can actually reconstruct the details of the original image. If we then put the two images side by side, the difference is startling. So, where has all this detail come from? Well, this fractal image is a prediction based on the digital data sampled at the original low resolution. And you can, of course, magnify this image just as much as you wish, because, like the M-set, it has infinite resolution.
What you see are fractal textures, fractal creations that mimic the missing data. They are, if you like, interpolations or predictions, but they're fractal, a greater and greater detail.
We're all used to seeing, every night on TV, the satellite view of the Earth with clouds moving over continents, showing the formation of storms and so forth. Now, those weather satellites have been operating for decades. What is not so well known is that there are also satellites up there, so-called spy satellites or reconnaissance satellites, which produce images of the Earth, or at least points of particular interest to the military, with thousands of times the definition of the weather satellites. But this means they have to transmit tremendous amounts of data to the ground, far more information than the weather satellites. So therefore, data compression, the ability to squeeze images, World War III has not yet broken out, and hopefully never will break out. Fractal geometry also has surprising applications in medicine. This is the blood circulatory system of the human body, and yet you'll recognize it. It is a kind of fractal. Now we can understand what is really happening when our blood circulates. Here is the most important fractal of all in the human body. A small portion of the incredibly complex wiring. We'll never understand how our brains work, but if we do, I suspect they'll depend on some application of fractal geometry.
Use the Force, Luke.
The same kinds of fractal design principles have completely transformed the magic of special effects.
This is a key moment from Star Wars Episode 3, where our two heroes have run out onto the end of this giant mechanical arm, and the lava splashes down onto the arm. My starting point here is to actually take the three-dimensional model and take essentially a jet and just shoot lava up into the air. This looks kind of boring. It's doing roughly the right thing, but the motion has no kind of visual interest to it. Let's look at what happens here when I add the fractal swirl to it. Where this becomes fractal is we take that same swirl pattern, we shrink it down and reapply it. We take that, we shrink it down again, we reapply it. We shrink it down again, we reapply it. And from here on, it's just a case of layering up more and more and more. I've used the same technique to create these additional lava streams. I then do it again here to get some just red hot embers. Then we take all of those layers and we add them up and we get the final composite image. My hero lava in the foreground, the extra lava in the background, the embers, sparks, steam, smoke.
designers and artists the world over have embraced the visual potential of fractals.
So a fractal is a geometric pattern that is repeated at every scale. It's coming from the Latin word fractus, which means broken or fractured. So the term fractal was first used by mathematician Benoit Mandelbrot to extend the concept of theoretical fractional dimensions to geometric patterns in nature in 1975. And the picture behind is from the famous Mandelbrot set, which we will be talking about later tonight. And so when we look at the fractal patterns, like there are two specific principles.
Yeah, I muted that mic. Go ahead, please. Go ahead.
All right, no problem. So yeah, there are specific two qualities of any fractal pattern. So the first one is self-similarity, and the second one is repetition. So a fractal pattern has to be self-similar and repetitive. So like when we look at the peacock, the wings of the peacock, and let's say leaves to the cauliflower, to the snowflake here, or the lightning, we will see that there is self-similarity and repetition. Let's focus on the leaf picture in the middle here, the yellow leaf. Now we see that there are these patterns which look like each other. They are not 100% identical, because in nature nothing is 100% identical, but only a similarity is enough for them. So they are similar and there is repetition. There are multiple of them. And when we zoom in, we will continue to see the repetition there. So this is the same for other fractal fields. It has to be self-similar and repetitive.
We could also play with words like self-embedding and scale
Yes.
invariant are synonyms there, perhaps.
Thank you. So now I would like to give you some examples starting from the micro level to the macro level. So, oops. Yes. When we look at the quantum field, the interactions of waves emitted by the electrons here, we see the fractal patterns here. They are similar to each other and they are repetitive. And this project was done by the Yazdani group in Princeton University. And this one is a Lichtenberg lightning. So this one is formed by high voltage dielectric breakdown in a plexiglass. These forms are called dendritic forms. These are also called branching. So wherever we zoom in this specific picture, we will continue to see this branching until the molecular level. And we also see these patterns in nature. Now I will continue to give you some examples from the plant life. These are, again, fractal plants, all self-similar, and there is repetition. And cauliflower, yes.
It's fun to think that perfect branching came to be the word Xi'an, which is where the word science comes from. And perfect branching is also behind the word divine, which is, it points to the spiritual. So perfect branching is a powerful electrical and spiritual metaphor. It's lots of fun.
Beautiful. Now, cauliflower is one of the examples that I love giving because it gives these qualities perfectly in your face. So we see this basic cone shape in the cauliflower. It's like a vortex. It's like a cone. And wherever you focus on this specific plant, you will see this cone shape repeating itself. For example, we focus on the side. Now we will see the same cones repeating. And on those smaller scale cones, we focus and we see even much smaller cones. So there is this perfect self-similarity and repetition. Some other examples from plant life.
So beautiful.
Beautiful flowers.
Inspiring.
So this is another example to the dendritic forms or branching. Now we see that there is this main trunk of the tree, and then we see the branches. It's getting smaller and smaller and smaller. Another example from bottom up, dendritic forms. And we can see them in nature, like in rivers. We see this main river and the smaller arms of the river getting smaller and smaller. And we can observe them. These pictures are taken by the satellite. Mountains, dendritic forms, fractal mountains.
Gorgeous.
And now I would like to continue giving some examples from the architecture. Starting from India, this is the Virupaksha temple. And we can see the patterns, self-similar and repetitive patterns here. This one is the Khajuraho temple in India. And I was able to find the plans of this architecture in Google. And here is on the left upper corner, in the figure A, we see this main model here. This is the main geometry. And in this architecture, they took this main model and they applied it in smaller scales, as you can see in B. And they repeated this action on the version C here in more smaller scales, which gave us a fractal architecture here.
There's lots of articles about fractality in African architecture, which seems to be global. And it's
Yes.
also about charge compression enabling the sacred. So it's a beautiful thing to study with electrical
Right.
metaphor.
That's what I was just going to say, the fractal architecture in Africa. This is one of the examples. This one is from Cameroon, Africa, the Mokulek settlement. We can see the fractal living spaces. This one is the Kitwe community in Zambia. These are hexagonal layouts we can see. Another one from Logonbirni, Cameroon, Africa.
Cameroon, nice. Nice.
And this one is the Baila settlement. This picture was taken before 1944, before the term fractal got modernized. So in the next slide, I will be giving you the plans of the settlement, and I would like to talk about it. So this is the Baila settlement, the floor plans. Now, when we look at here, we can see the perfect fractal architecture. Like on the bottom picture on the left, we see this main geometry is repeated in smaller scales in the middle here. We can see them. And even one more level, it's even more in smaller scales. They installed the same geometry. So exact same design on 3 different levels. And Daminter also talks about it in the fractal architecture videos, like on how to create the perfect fractal fields, architecture, buildings. Of course, there are a lot of principles that needs to be applied, like first mapping the magnetic fields of the landscape, and then working on the plans which are based on golden ratio, and then using the organic material and so on. But I just want to give some basic examples right now, because we don't have a lot of time for the deep science here. Now all these informations, we can see them in Ron Eglash's YouTube video. He has beautifully presented all the fractal designs in Africa, and you can search it on YouTube if you are interested in fractal architecture. He has laid out the details here. History of the golden ratio. So Egyptians have used the golden ratio in the design of the Great Pyramids. Maybe it was used before, but we don't know that, so we could only see some of the structures who could still survive today. Greeks have also used the golden ratio in the design of the Parthenon. Plato, in his views on natural science and cosmology, presented in his Timaeus, considered the golden section to be the most binding of all mathematical relationships and the key to the physics of the cosmos. Now, I would like to read this again. So, Plato considered the golden section to be the most binding of all mathematical relationships and the key to the physics of the cosmos. I think this is quite strong. Afterwards, right afterwards, Euclid, in his book Elements, he referred to dividing a line at the 0.618 point as dividing a line in the extreme and mean ratio. Now, this gave rise to the use of the term mean in the golden mean. He also linked it to the construction of a pentagram. Now, this one is also very interesting because today, whichever school we go to or wherever we go, and we ask any student or anybody to divide a stick into two. Let's say we have a stick with a specific length, and we ask them to divide this into two. They will try to divide it from the middle point. But what Euclid suggests is that if we divide this from the 0.618 point, which is slightly off the middle, that will be the extreme and mean ratio. So we can clearly understand that the understanding of the mathematics and the geometry was much different than our current time. So Leonardo Fibonacci discovered the unusual properties of the numerical series that now bears his name, the Fibonacci sequence. We will talk about it. And Leonardo da Vinci provided illustrations using the golden mean extensively for a dissertation published by Luca Pacioli in 1509 entitled The Divine Proportion. Well, in this book, Leonardo da Vinci also presented some artwork about the Platonic solids and the very famous Vitruvian Man. Johannes Kepler, the discoverer of the elliptical nature of the orbits of the planets around the sun, also made mention of the divine proportion, saying this about it: geometry has two great treasures. One is the theorem of Pythagoras, the other the division of a line into extreme and mean ratio. The first we may compare to a measure of gold. The second we may name a precious jewel. Now, very simply, let's see how golden mean ratio is calculated. Let's say we have a stick and this stick's length is 1 unit. As Euclid suggested, if we cut this stick into two from the 0.618 point, which is here, now we would get 2 sticks. And the 2 sticks ratio to each other would be equal to 1.618. So on the next slide, we will see the 2 sticks here. We see them here. And when we divide 0.382 to 0.618, we get 1.618, which gives us the golden ratio. But the numbers doesn't need to focus on specific numbers like 0.618. We can have other set of numbers, something like this. Let's say we have 7 and 4.3. This can also give us the golden ratio, as long as the proportions allow us. Let's see another example. Let's say we have 7 units and 5 units. And 5 divided by 7 would equal to 1.4. And is there golden ratio? No. This is a very basic example about calculating the golden ratio. Now let's look at another example here. We have a set of numbers, set of sticks, let's say 1, 2, 4, and 8. Now, in order to understand if there is a golden ratio relationship among these numbers, we have to either divide them to each other. Let's try it. Let's divide 8 by 4, which would equal to 2. It is not 1.618, so there is no golden ratio here. 4 divided by 2 would also equal to 2. This is not 1.618, so there is no golden ratio. Or we could also use this method. Let's multiply any of the numbers here with 1.618. If the result gives us the following number, then it is golden ratio. If not, then it is not golden ratio. So there is no golden ratio in this set of numbers. I'm sorry. Let's look at another example here. We have another set of numbers starting with 0.382, 0.618, 1, 1.618, 2.618, 4.235. So let's apply the same principles here. Let's multiply them with 1.618. When you multiply 382 with 1.618, you would get 0.618. This is golden ratio. And when you multiply 0.618 with 1.618, you would get 1. And do the same thing, you would get 1.618, and continues like that. So there is a golden ratio relationship in this set of numbers. So golden mean ratio is the only number in the universe which have both arithmetic mean and geometric mean. So when we say arithmetic mean, if you add the first number to the second number, you will get the third number. Do the same with the second number and the third number, you would get the fourth number. And it continues the same. So this is called arithmetic mean. And geometric mean is when you multiply any of the numbers here with golden mean ratio, which is 1.618, you would get the next number. So this is called adding and multiplying constructively. And we will be seeing this science, this mathematics here in concepts like phase conjugation and constructive wave interference. So this is a very basic picture here, which we will be talking about it in later sciences. We see that the waves interfere with each other at specific levels, which give us the golden mean ratio. As we said, golden mean ratio is the only ratio which has arithmetic and geometric mean. Because of that, only golden ratio allows adding and multiplying constructively. Now, this is also called, as I said, constructive wave interference. I will get back to this slide later on tonight. Now, let's continue with the star symbol here. The star symbol, or the pentagon inside, is one of the most sacred symbols in history. And the star symbol has perfect golden mean ratio in every part. Let's focus on the red line here and divide it to the yellow line, the distance of the yellow line. And that would give us 1.618. And we do the same with the yellow line and the blue line here. The result is 1.618. And then divide the blue line with the pink line here. It would give us 1.618. And furthermore, if we decide to draw another star in the pentagon here, something like this, this would allow us to track the golden ratio going through the wormhole. So this is like an implosive field where the golden ratio repeats itself until infinity.
It's beautiful that you summarize this way, Tufan. And I just wanted to say that, you know, it was shocking to me when we realized that all the geometry people knew that golden ratio was a solution to arithmetic and geometric progression. But none of the electrical people or physics had come to the conclusion that it in fact then also explained constructive interference and therefore solution to compression. That concept is not in the conventional physics literature. It was our work that first pointed out that constructive compression and constructive wave interference is the problem golden ratio solved. And no one had simply looked at that before, which was actually shocking because it's the solution to so many problems. So again, I'm delighted to hear you reviewing it here. Thank you.
Yeah, you're welcome. It sounds like it's one of the hidden secrets, but
Really?
It's nice that this information is coming out now.
Yes, and it's specifically the solution to implosion, which is therefore negentropy. This is a powerful thing. It's wonderful to hear this expressed in other terms. Please go ahead.
Yes. So I'd like to show how to draw a golden mean ratio spiral with a star. So we start with the top corner here and continue drawing the spiral. We pass the second edge, and then we go over the third edge, and then the fourth edge, and then the next interference point, and continue the spiral, and we will have the golden mean ratio spiral through a star. And we can also draw that by a golden ratio rectangle. Now, in order to have a golden ratio rectangle, we need to have the specific ratios. Let's say we have 1 unit here, and this side has to be 1.618 in order to have the golden ratio. And as Euclid suggested, we would need to cut this rectangle into two from the mean and extreme ratio, which is somewhere like this. So when we cut this golden ratio rectangle from the mean ratio, from the golden ratio point, we get one perfect square and another perfect golden ratio rectangle. Now this is the second golden ratio rectangle that we have. The first one is the bigger scale, and the second one is the smaller scale. And the fun part is that we can continue doing this until forever. So we would need to apply the same principle to this rectangle here. Cut it in the mean ratio, and then we would get another perfect square and another golden ratio rectangle, something like this. So we would have perfect squares continuing like this. And then if we apply the quarters of the spiral to each square, we would get something like this. Now the spiral follows the squares, as you can see, and goes with the golden ratio. Now, I'm sure there are other ways of drawing a golden ratio spiral with other geometries, but this is one of the easiest ways that I find. And we see these spiral patterns in the universe in many different scales, from micro to macro. Like in the galactic scale, we see them on hurricanes. And there's this beautiful relationship between the Earth and the Venus. Every 8 years, the orbits of the Earth and Venus, they create that perfect star or the perfect rose. Now, there's a very nice video of that on YouTube. I'm not going to show it to you, but I'll just post the link here to the chat box, so you can watch it if you want. It's a short video how Earth and Venus create this beautiful star in 8 years, every 8 years. And
the Earth and Venus orbit duration are exactly exact integer exponent golden ratio times Planck time as well.
yes. Now, Kepler first mentioned about the Platonic solid relationship with the in the solar system. But if you check the website of Spira Solaris, you will see in great detail the golden ratio and Fibonacci connection of the orbits of the planets in the solar system. It's a great work done. Spirasolaris.ca, and let me write it here as well.
And it's so interesting that it's a very easy step of logic to see that if golden ratio perfect embedding is the geometry of orbital nestings, that is therefore how gravity is stabilized.
Right.
Perfect compression.
So we can see the Fibonacci sequence here. We will talk about it more, the Fibonacci sequence, but let me just show you because we have the slide now. 1, 2, 3, 5, 8, 13, 21, 34. Now we see the golden mean ratio scales in our body, in our arms, our hands. And let's talk about the Fibonacci series now. Now, Fibonacci series are a way of nature mimicking the golden ratio, because we know that golden ratio is a number, is an irrational number. It's like 1.618. The nature, like if let's say we have a tree and the tree needs to give a branch, now it cannot give 1.618 branch. It can either give 1 or 0 or 2 or 3. So it cannot give point values. So the nature needs to follow the whole numbers. So it goes like 1, 1, 2, 3, 5, 8, 13. And when you add any number to its neighbor, you would get the following number. So 1.1, 2, 1.2, 3, 2 plus 3, 5. You can see it on the left screen here. And the interesting thing is that as you go through the Fibonacci numbers, Fibonacci sequence, it perfects itself towards the golden mean ratio. Now, how does it do it? When we divide the numbers that I presented in the previous slide to each other, let's say 1 divided by 1 is 1. 2 divided by 1 is 2. And then the next one, 3 divided by 2 is 1.5. And the next one, 5 divided by 3 is something like 1.666, I guess. And I think 8 divided by 13 is 1.6. And it goes like this. As you can see, it kind of perfects itself towards the golden ratio. And when we look at the branching patterns, we see, let's say this main trunk is 1, and we see 2 branches, 1, 2, and the next number is 3, 1, 2, and 3. The next number is 5, 1, 2, 3, 4, and 5, and it continues like this. When we look at the leaves, it follows the same principle. 1, 1, 2, 3 in this level, 5, and 8 leaves. And when we look at the plants, the number of petals also follow the same principle here. 1 petals, 2 petals, 3 petals, 5, 8, 13, 21, and 34. Now this picture is taken from the Scientasia website. If you want to check it, you can check it.